In this video, we're going to continue to cover the HVAC system on your heating system. Customer complaint is that there's insufficient heat. So this is not a no heat situation. This is insufficient heat. One of the first things that I typically look at is the thermostat. Put the scan tool on there, start the vehicle up, feeling the upper radiator hose. When the upper radiator hose opens, take a look at the temperature. The thermostat's typically open about 190, 195. If it's opening up at 170, that can be the cause. You can also have a heater core or a heater passage that's plugged up. This typically happens when you look at the coolant, it looks like rust. You can try to reverse flush the system to clean that out, or replace the heater core or whatever the part is that's plugged up if it's one of the hoses. Got to be careful with doing this for some customers because you can reverse flush it, clean it out, and there's just so much junk inside there that it'll plug up again. They take it to another shop, they get it fixed there, and then they're going to turn around and sue you because they paid you a bunch of money to fix that and it was broke again in a couple months, and a judge doesn't understand automotive very well, so they're most likely going to award them that you have to pay them their money back. The temperature door stuck in the position, that can be caused by multiple reasons, whether it's being controlled by a cable, by linkage, by the vacuum control, or by one of the motors. And then you can also have low coolant. For no heat at all coming through there, one is coolant dangerously low and their engine is probably overheated already. Heater core passage completely plugged up. Again, you can try to reverse flush or replace it. Or the temp door stuck in the full cold. And again, multiple causes from that. You'll have to follow through and diagnose it. This is the one the customer brings the vehicle in and they're saying, hey, I turned my heater on or turn the vent on, or when I start the car up, the windshield instantly fogs up. Instead of defrosting, it fogs up. You'll usually get that sweet smell inside there because the heater core is leaking. If you're at that point, heater core's got to be replaced. Heater is stuck, or if the system is stuck in a vent position or defrost or heat, or one of those modes will not work. Again, you can have multiple causes for this, but on a lot of these newer systems, the motor, and that's what you're looking at in the lower left-hand corner, those go bad and need to be replaced. Now, don't immediately assume that that's bad, because you can have a computer that controls it that goes bad. You can have a wiring problem. So you need to follow your diagnostic procedure and then replace that. Some of them, man, it's a 15-minute job in and out. It's really nice. First one that I did was on an older Taurus, and it was 3 bolts holding it in, 2 bolts you could get. The third bolt, you had to pull the entire dashboard out in order to replace it. And just to get that last little screw ended up being a 6-hour job. For the blower motor, we're going to go through fairly quick here. I'm going to show you, this is an older diagram, but most of the newer diagrams, they don't show it to you on one page. So this is one they have it on one page, so I'm still going to show it to you this way. So upper left corner is power. Down at the very bottom is ground. This is a Valley Forge style schematic, so power just flows from top down to the bottom. And power goes to your HVAC switch. So in the off position, blower motor is not going to work on this vehicle. Some vehicles, if the key's on, the blower motor will run on low. But this one, you have to turn it on to one of the modes in order to get power to come to the fan. So first position we're in, so we have the HVAC system on. The blower motor switch is in the low position. And now following that dark blue wire, power goes to those 3 resistors, which is called the resistor block. And show you the image of a resistor block on there. So voltage supplied there goes through all 3 resistors. Voltage drops with each resistor. So we're going to drop the voltage 3 times before it gets to the blower motor, and with the low voltage, blower motor is going to run on low speed. Now move into the medium-low position. And on this one now you can see we're going to bypass one of the resistors, so we're only going to drop the voltage twice before the voltage is applied to the blower motor. Blower motor is going to run a little bit faster. Medium-high position. Now we're going to use just one resistor, so only one voltage drop, and again, blower motor runs faster on this position. Now on this one, again, this is older GM system where GM is using a high blower relay. On all the newer systems, that blue line that goes down to the relay would actually go directly to the blower motor. But this one has the red line. You can see full battery voltage applied to the blower motor, so the blower motor is going to run on high speed. Now, this is the way the manufacturers have done it for decades, with the resistor block and the blower motor. On some of the newer systems now, they got much more complicated with computer controls and duty cycle going to the blower motor. You're going to have to get into the computer operation to see how those work. Every one of those that I've worked on that the blower motor did not work, it was the blower motor assembly that needed to be replaced. So here's another image of a newer blower motor, or I'm sorry, a new resistor block, and the arrow is pointing there to a thermal fuse. So that thermal fuse is inside the smallest of those 3 resistors, which that's the one that's going to get the hottest. And if that gets too hot, that thermal fuse is going to pop open and you lose your low, medium high positions, and you only have blower motor in the high position. So customer brings the vehicle in with blower motor only working in the high position. It's going to be typically this resistor block that's gone bad. Now, if you replace just the resistor block, you're going to blow it out again. The reason that thermal fuse blows is because your blower motor is starting to go bad. From the last video, I showed you that that blower motor is out of balance. It has that heavy fan on one side, nothing on the other side, so those bushings inside there will wear out. And with a DC motor, the slower the motor turns, the higher the current flow. The higher the current flow, the hotter these resistors are going to get, and that's what causes them to burn out. So when you have one of those thermal fuses blown out, you need to replace both the resistor block and the blower motor, or you're going to have a comeback. Now to get into the AC system, and to get in the AC system, you have to understand BTU. So BTU is a British thermal unit. It is based on raising the temperature of 1 pound of water 1 degree. So to raise the temperature of 1 pound of water 1 degree, it's 1 BTU. To go from 32 degrees Fahrenheit just before it turns into a solid, so we still have a liquid. So it goes from 32 degrees liquid to 212 degrees just prior to it changing from a liquid to a vapor or boiling. We're going to go up 180 BTUs. So 212 degrees, where we end at, minus 32 degrees we started at, there's our 180 degrees that we're going to raise the temperature, meaning it's going to absorb 180 BTUs. The next part you need to understand besides BTU is also latent heat. And this is heat that can't be measured with a thermometer. So if you take water 32 degrees solid and change it to 32 degrees liquid, so temperature didn't change at all, it is going to absorb 144 BTUs just to change from a solid to a liquid. Again, at the other end of the scale, to raise the temperature, or starting with the temperature at 212 degrees liquid and changing it to a vapor still at 212 degrees, that water is going to absorb 970 BTUs of heat energy. So I've got highlighted here a tremendous amount of heat energy just to get it to change from a liquid to a vapor. Now, to convert it back to a liquid, it has to again give out that amount of heat. So this is going to become important to understand the amount of energy required to change it from a vapor to a liquid or a liquid to a vapor, and what they're talking about with latent heat and BTU. Now, on this one here, we've got a cube, so say 1 cubic foot of air that's relatively cool. As we start smashing this down or squishing this down, so go from 1 cubic foot down to 1 cubic inch, we still have the same amount of air, but now it's under a high pressure as we compressed it down. The temperature of that air is going to get hotter and hotter the smaller you get, because even though it's cool, it still has a certain amount of heat energy in it, and what you've done is you've taken that heat energy, put it into a smaller area, and so the temperature is going to go up. So, before moving on, make sure that you understand BTU and latent heat. So a few of the things to know: heat flow. Heat will always flow from a warmer object to a cooler object. Pressure and boiling point. If you raise the pressure on a substance, you will increase the boiling point. And relative humidity. So air, the warmer it is, the more moisture it can handle. That's the reason that things begin to cool down at night and a dew begins to form or fog will begin to create, because the air can't hold as much moisture as it cools down. So it's going to give up that moisture in droplets. And conversely to that, as you warm it up, it's going to be able to hold more moisture. With our refrigerants, R12 was developed sometime back in the 30s. It started becoming popular. Everybody thought that, oh, this is the greatest thing since sliced bread. Sometime in the 50s, they started putting the refrigerant into the cars, and I tried looking this up, found several different sources that said different vehicles were the first to put it in. I finally just gave up. All of them agreed it was sometime in the 50s, but who it was and which year was first, I don't know. So in 1994, the R12 was phased out and replaced with R134A. Now, when R134A was being introduced, they knew that this was a stopgap, that this was not the final answer, but this was a refrigerant that we could use until we got a final answer. So some manufacturers started using the R134A in model 1992 model year, and it had to be used exclusively by 1994. You can convert an R12 system into an R134A system, so there's a procedure for doing that, and it can be safely done. The R134A is not as good a refrigerant as R12, so when you do that, the AC system's not going to work quite as well as it used to, but it'll still work good. The newest refrigerant that we have for the automotive industry is the HFO 1234YF. I'm typically going to refer to it as R1234. So Cadillac was the first manufacturer to use this in 2013. It is now required for all the manufacturers to be using this in the U.S. and I think the European Union is also requiring this now or soon will be. So this is the refrigerant that more and more cars have as we progress on. The good news is that the R1234 works almost identical to the R134A. So if you know how to diagnose an R134A system, you won't have any problem with the R1234. Another refrigerant is R744, which is CO2. Daimler and BMW really wanted to have the CO2 as the refrigerant instead of the R1234. For me personally, I'm glad we didn't go with it. Your CO2 runs at very high pressures, 1800 to 2400 psi, whereas on the R134A system, we're dealing with pressures typically less than 400. It also requires a secondary cooling system. Because if you have a CO2 evaporator in the passengers or under the dash, and then all of a sudden springs a big leak, the CO2 is going to replace the oxygen inside the vehicle, in the cab of the vehicle, and you're going to kill the people that are in there. So between the high pressures and requiring a secondary, I don't believe that it was going to be as efficient as a R1234 system. The reasons that we've been changing the refrigerants is two reasons that you need to understand. One is the ODP, or ozone depletion potential. The other is the GWP, or the global warming potential. So R12 had CFCs in it, which in the 50s, the 30s, the 40s, back in there, when they thought that the R12 was just a great thing and they were just letting the R12 escape into the atmosphere, they eventually figured out that that's what was depleting the ozone layer. The global warming potential is what they're accusing of causing global warming, which when we went for nearly a decade without any global warming, they changed that to global climate change. But they've taken a light, take an aquarium, we put oxygen in there or air in there, and it'll warm up with that light. If you add CO2 to the mixture, it'll warm up more. So they know that the CO2 can contribute to warming. The R12 has a global warming potential of 10,900. So really bad for global warming. As it escapes into the atmosphere, it stays in the atmosphere for a long time. Ozone depleting, yes. So the R134A, you can see a global warming potential of 1,400. So a whole lot better for the environment than the R12, but still not real good. Did not have the ozone depleting. Now the R134A, when it escapes, this doesn't stay in the atmosphere near as long, which is part of the reason it has that much lower number. The R1234 has a global warming potential of 4. So that's the reason it qualified as the new refrigerant, and it works very similar to the R134A. The CO2 744, or the R744, has a global potential of 1 because the CO2, or the global warming potential, is based on CO2. That finishes up the second video. You'll want to watch the third video as we go on for the rest of the HVAC system.